Okay, good morning, everyone, and welcome to the Nano-mechanics course. In this course, we are going to have an introduction to nano-mechanics, which is an important branch in nanotechnology, and it has very different application in different areas of science, including are you structural or structural students? Also in structural engineering, including the health monitoring of buildings using nanocomposites, and in aerospace, and also in aerospace industry, in automotive industry, in marine industry, and a lot of other applications. We are going to focus on modeling techniques in nanomechanics. The modeling techniques include continuum modeling, atomistic simulation, and also multi-scale modeling, which is a combination of continuum modeling and atomistic simulation. Actually, due to the program of the course today, we were going to talk about more these modeling techniques with a focus on continuum modeling, but this is the topic of lectures of Dr. Tuna, that unfortunately today she's sick, so hopefully she recovers. She's going to tell you her lecture tomorrow. But today we are going to talk a little about multi-scale modeling and atomistic simulation, with a special focus on molecular dynamics simulation. It is a very famous technique for atomistic simulation. And hopefully in the last day, we are going to learn LAMS. That is the well-known software that is usually used to apply molecular dynamics. I hope that the last session will be something like a workshop, so you will write your own script and you can do your very first project. Okay, I just introduce myself. I'm Razia Izadi. I have a PhD in mechanical engineering. And since 2020, I had the honor to collaborate with Professor Travalucci and Dr. Tuna, where we have conducted several research projects. And my main field of expertise is nanomechanics, with atomistic simulation and multi-scale modeling, in which we try to find the mechanical properties of atomistic simulation using molecular dynamics, and also find continuum equivalence frameworks that can mimic the observed properties in atomistic simulation. Sometimes we use just classical theories to mimic the observed behavior, but sometimes in the classical theory there are some abnormal behavior that can be described with classical theories, so we use more enriched continuum theories. Okay, before starting, let's just talk a little about where does molecular dynamics stand in the world of simulation techniques. Below 1 nanometer and 1 picosecond, we call it subatomic scale. And here, the simulation techniques that is mostly used is quantum mechanics, which is based on solving Schrödinger equations. It is so exact, but it can simulate 1 to a very, very small number of atoms. Then in the range of about 1/10 of nanometer to around 100 nanometer and less than nanosecond, we have the nanoscale. And we have two famous simulation techniques, which is molecular dynamics that we are going to explain thoroughly, and Monte Carlo that we are going to explain a little briefly. But for example, in the nanoscale, we cannot simulate directly, for example, a microsecond. Because in atomistic simulation, in molecular dynamics, our time step is 1 femtosecond. 1 femtosecond, which is 10 to the power of -15 seconds. But for example, 1 microsecond is 1 to the power of -6 seconds. Okay, so we have to have 10 to the power of 9 steps that we have to integrate around sometimes 1 or several millions of atoms. So it is not really feasible, but there are some techniques called mesoscale, in which something like force framing, that we use the data from nanoscale and we adapt it for higher scales. And 1 micro And for that 1 meter per second, we have the macro scale, okay? And we have a lot of simulation techniques for that, for example, finite element simulation. What is multi-scale? Multi-scale is bridging between these scales, okay? So we use the data from a lower scale, and with some methods, we adapt it in higher scales so that we can extend the time and length scales. Okay, I just brought some examples of every simulations. This is the problem of crack propagation. In a mathematical ways, we are trying to do something like this for your project in the last day. And we also have another indentation. You know, we have indentation in mechanics that we have a mandrel, we put it on the surface. But in nano-indentation, we also have another indenter, nano-mandrel that comes on the surface. And with the force between the nano-mandrel and the surface, we can extract some properties about the structure. Okay. Okay, we also have, for example, a nanowire under tensile deformation. This is a nanowire. Of course, you know, the length is infinity, but we show a small part of it. It has a rectangular cross section and it's under tensile deformation. It is some property that is only observed at nanoscale, because under tensile deformation, it has kind of twists because of its internal structure and its size. Also, it is a dynamic problem. We have a projectile that comes out of the surface. The fabric is actually composite made of ceramic and polymer. So, just as an example, I brought some examples for chemistry, which is the interaction of protein and membranes. Okay, I told you that we have two main simulation techniques in atomistic simulation. The first one is molecular dynamics, and the second is Monte Carlo. Molecular dynamics is a deterministic method. It means that at every time you can know what's the state of the problem. Okay, you can track the system in time. But Monte Carlo is more stochastic method, and it's used when you want to find the equilibrium state of a problem. So that's why molecular dynamics is much more used than Monte Carlo. But we have heard that Monte Carlo was initially developed to find the numerical integrations. For example, it is one of its famous applications is to find the pi number. If we have a rectangular a square in which we have a circle, and we, for example, drop some points randomly to the square, and then we calculate the number of points that are inside the circle to the total number of points. As we increase the number of these points, the value tends to pi over 4, which is actually the area of the circle to the area of the rectangular. It's quite simple. You can also do it yourself and see that after some increasing the number of atoms, it converges to pi over 4. Okay, but in atomistic simulation, how do we do that? We have a number of atoms, We select a number randomly. Then we evaluate again the potential energy of the system. We're going to talk about the potential energy much more, but we evaluate the potential energy. If the new configuration has a less potential energy, it means that it is more near to equilibrium than the previous one, because the system tends to decrease its potential energy. So the move is accepted. But if it's not, what is it? But if it's not, again, we cannot say that it is not accepted, because in nature, sometimes something happens that it doesn't really to equilibrium, but for example, we have fluctuation. Sometimes the energy increases, sometimes the energy decreases. So we find from the difference between these two, we build the Boltzmann factor of this, or we build a factor that is between 0 and 1. Okay? We make a random number. Okay. For example, now we know that the new energy is more than the old energy. Okay. If they are somehow near to each other, this is 0, so this is 1, and it is more probable that this is more than the random number. Yes. But if it's so far from this one, it means that it really increases the potential energy. The difference between these two tends to infinity minus infinity, so it goes to 0, and it is more probable that it's less than the random number. Okay, so it's somehow a stochastic number, but as I told you, it is for finding the equilibrium state of the problem. Okay, but now what is molecular dynamic? Molecular dynamic means that you want to simulate the motion of a group of atoms with time. How? By integrating the classical Newton equation of motion. It means that we write Newton law for each of these atoms to find how they are moving with time. The first thing you need to know is the initial configuration of the atoms. Okay, it can be any initial configuration. We label each atom in molecular dynamics. Each atom has a label because we are tracking it, and then we have a position vector. Okay. And then we should have an initial velocity. The initial velocity, what do you think it depends on? The initial velocity of the atoms. Okay, the velocity of the atoms. Temperature, yes, of course. When the temperature is higher, the velocities are bigger. When the temperature is lower, the velocities are lower. But how we can, just adopt an initial velocity to the system so that it can simulate our temperature? This is actually one of the methods, one of the famous methods to devote the initial velocity. It is the Maxwell-Boltzmann distribution. Maybe you have seen it before. For each temperature, we have a different distribution. For example, in 300 Kelvin, which is around the room temperature, this is the curve. The green one is the curve. And for example, it tells you that the range of the velocity is from 0 to around 1000 per second. But if you want to know what is the probability of this velocity, you can find it on the curve. You find the probability. For example, you have 1,000 of atoms. This is the probability. You multiply it, and you understand how many of these atoms should have this velocity. Okay, so in average, these velocities can make the initial temperature for you. Of course, this is not the exact, but you can even, there is a theorem that says that, for example, for this temperature, this is the mean value of velocity. You can give this mean value to each of them. Of course, they cannot have a direction because in that way, the system is moving. It's not related to the temperature, but they can even the same velocities, but the time to relax the system increases. But this one, because it's actually a natural distribution, it is a Gaussian distribution. Number does not. Here is how we get the initial velocities. Okay, now that we have the initial velocity, we need to know how the atoms interact with each other. Okay, this is actually the interaction energy between them that defines the material. That, for example, something is liquid, something is solid, something is transparent, something is not. Okay, because in molecular dynamics there are a bunch of spheres, rigid spheres just interact with each other, collide with each other, and go far. So we have to understand what is the interaction energy. This topic is a little related to chemistry. I'm going to just give you a brief overview. We have two types of interactions. We have intermolecular non-bonded and intermolecular interactions. The intermolecular are the interactions that are between the molecules or between the atoms in different molecules. And intermolecular are the interactions within a molecule that puts the atoms together. Okay, we have different, each of them has different categories. Are any of them familiar with yours? For example, do you know what is covalent bonds? The covalent bonds is when they share the electron cloud with each other with some electrons. And the metallic bond, actually, it is not kind of a bond. We sometimes refer to it as electron C, because we have some electrons that are freely moving, non-localized, and we have some compounds, and they are just, moving around the neutrons. That is why they are passing electricity and also heat. And they have ionic, when an electron comes from an atom to the other. Okay, and then one of them become positive, one of them become negative, and they just attract each other. And we also have intermolecular. Are you familiar with van der Waals? It is between two atoms that do not share a bond with each other. It can, for example, if this is I don't know, for online students, maybe it's also better that I explain on the screen. Oh, yes. Okay. For example, this atom, it has a covalence bond with the atoms around it, but this atom with this atom, they have the van der Waals interaction. Also, this atom, for example, with an atom that is far from it, that they do not have an exact bond, it has also a van der Waals interaction. So sometimes you are just simulating a molecule, but you still need to include the van der Waals interactions. And we have electrostatic. It's different a little from ionic because it is related to the partial charges in the atoms. You know that in some atoms, some molecules, an atom has more electronegativity and the other has less electronegativity. So the one with more electronegativity just attracts the electron cloud to each other. So it has a partial charge, for example, about 1.2 charge, positive charge on one side, 1.2 negative charge on the other side, and they have electrostatic interaction with each other. But let's just take this. And these three parts, the covalence, the van der Waals, and electrostatic, are usually combined in molecular mechanics. Maybe you have heard of it. It's actually a force field, a kind of interaction that is described, and it can be used in molecular dynamics. It has different terms. It has bond, angle, dihedral, and inversion. They are different degrees of freedom that they contribute to the potential energy of the system. Okay, then they are changing. We have bond, which is between two atoms. We have the angle, which is between three successive atoms with an angle between them. We have dihedral. I don't know if it's understandable when it's dihedral. We have a plane from the first three atoms. We have another plane from the last three atoms, and the angle between these three atoms, these two planes, is actually the dihedral. Okay, and we also have inversion. Okay, inversion, of course, it is actually the angle between the first plane, which is from these three atoms, and the plane between the one which is a little off and the central atoms. But we usually do not have inversion. Sometimes we add it, for example, if you know the aromatic rings, for example, in some carbon structures, to force that it's planar, we define such a degree of freedom for it, so that if it comes off, it increases the potential energy and forces it to just goes down and have a plane surface. And this is the non-bonded interaction. It comes from electrostatic and van der Waals. So each of them has, of course, their mathematical representation. They can be very different. We are not forced to consider a strict, and this is where we have different molecular mechanics. You may hear that a lot of names under the title of molecular mechanics. For example, we can consider a linear spring between them, so that the energy takes the quadratic form. Okay, and we have a parabolic here. Of course, for example, it is right when we are near the equilibrium position. Why? Because if the distance between the atoms increases, in reality, the bond breaks. But here, no, again, the potential energy increases. Also, we can have the same quadratic form for the angle, and the parameter K here shows the stiffness of the bond, okay, and also the angle. And as it increases, it means that it is harder and we need more energy to just take the atoms apart from each other. Okay, and for the dihedral, as we have a harmonic periodic case one, we have two planes. If you rotate one of these, again comes back to the situation. So we have one. And for the inversion, as I told you, we also have a harmonic just to make them to be on the plane. It is for the electrostatic. It's a quite familiar relation, and also for van der Waals. This is Leonard Jones' actually prediction of van der Waals. It composes of two terms. The first one is this part. with the power of 12 is the repulsive term, and this one is the attractive term, okay? And the combination between these two makes this curve which has an equilibrium position, okay? Of course, you know, this term, I mean, the parts relating to the attraction is actually come from quantum mechanics, and it's exact. But this part, no, we do not have, for the repulsion term, we do not have an exact term. We just know that the energy goes to infinity, and we have a strong repulsion. It is just because, you know, it is they have to the power of 2, and it is for better calculation, easier calculations. Okay, so as I told you, depending on the force field we choose, and depending on the function we want to describe what we have seen, we have different force fields. For example, these are the famous molecular mechanics. You may hear it, John, Amber, and it's actually the molecular mechanics. There are some force fields that are specialized or some specialized. For example, for cadmium, germanium, and silicon, we have tertiary potential. We have AIV and Brennan potential for just cadmium. And for metals, it is one of the most, EAM is one of the most famous force field. Also for unit, we have Buckingham and a lot of other force fields for different atoms. Okay, we are going so fast. Okay, after we find, okay, so now we have the initial position, we have the initial velocity, and we have the interaction energies. What do we do with this interaction energy? Yes, we calculate the force. What is the relation between the energy and the force? It is the derivative. It's the derivative of it. So now that we have the potential energy in terms of the position of the atoms, we can find the force exerted on each atom by the other atoms. Okay, with the derivative of this. Sometimes we have analytical derivatives, for example, for EAM, but sometimes we need to do the numerical. Is the part that is mostly expensive, and it needs a lot of computational expense, and it takes 80% or sometimes 90% of the computational cost. So a lot of techniques are used to just decrease this amount of computational cost here that we'll discuss about it. Okay. So now that we have the force, we write the second law of Newton for each of the atoms. Okay, for each of them, we write the second law of Newton. So we have the force, we know which atoms we are, so we have the mass. So what do we find? The acceleration. Now we have the acceleration, we have velocity, and we have the position. How can we predict the next step? Using integration, yes? So we have these three quantities at time t, and we want to find them at a time step after that. Most of the time integration methods are based on Taylor expansions. Okay, we know that, for example, this is a simple Taylor expansion for the position vector. We have the first derivative and we have the second derivative, some terms that we are neglecting. The first derivative is actually the velocity, and the second derivative is acceleration. Okay. The simplest idea is that, for example, we find the vector position at time t plus delta t with the position of time t and its velocity. And also we find the velocity of time t plus delta t with the velocity and the acceleration. Okay, it's quite simple. And then after we find this, how can we find the acceleration? After we find the Ri and the R, you know, we find the position, and with the position, we can find the potential energy. Then with the potential energy, we find the forces. With the forces, we find the acceleration. So if we have the position, we have the acceleration. Okay, so from this point, we reach to this point. Okay, but the problem is that the Euler method is quite unstable. the order of error in other method is really high because we are neglecting a lot of other terms. So this is not usually used in molecular dynamics. We have so many different methods, but the most famous and popular one is velocity barrier, which decreases the error of simulation so much. For this, we use all the third term to find the position and time equals the future position. Okay. Then with the future position, first we find the acceleration. Then we find it is why it's called velocity barrier. Then we find the velocity at the middle of the time step. Okay. We find the velocity at the middle of the time step, and then we find the velocity, the new velocity with the velocity at the middle of the time step, the new acceleration. So it is a little combination between these. But this is, as I told you, so much popular and it's still working, and it's actually usually the time integration that is
the velocity at the middle from the previous acceleration.
Yes,
and we use the acceleration.
Yes, but for the end velocity, we use the acceleration of the end velocity of the middle step, for which the velocity of the middle step is come from the acceleration. Okay, so we are using so many data to improve our prediction. Okay, but how much delta t should be? How much should be our time step? It depends. If it's too small, what will happen? Yeah, we have a lot of computation. We should some wait for a long time and nothing happens between them. It's two chains of, for example, materials, and we see that after sometimes nothing happens. But what if it's too big? We will lose some information about it. Now, something will happen and we don't understand. For example, even the atoms may just collide with each other. They just can't. So we have to find a proper time step. At the end of the story, the proper time step for molecular dynamics is around 1 femtosecond. Okay, but it sometimes differs to the case by case. Rule of thumb says that the time integration time step should be 1/10 of the smallest period in the system.
Can I ask you a question of the time integration, but with a more complex system? If we use a constraint variables, is there a relation between the time integration and the mathematical relation between the time integration and the stiffness of the constraint, or there is just an empirical approach?
Very good question. But we are going to talk about it. Yes, actually, we have some constraints on the system. For example, we want to, set the temperature. Yeah. We want to set the pressure. We have to interpret these equations. So the form of integration methods will change. Okay. The basic is the same, but the form will change. I will show you. Okay, so it should be 1/10 of the smallest period in the system, so that we do not lose any interactions. And the smallest period actually in the system, which is related to the highest frequency, is usually for the smallest and lightest atom, which is hydrogen. Okay, and its period is about 10 femtosecond. So that is why the time step. No, I haven't said. So that is why the time step in molecular dynamics is usually 1 femtosecond. But we have a table, for example, for these kinds of atoms. However, if, for example, the temperature of the system increases, we have to decrease the times because the system moves faster. Okay, now relating to your questions, if there is no constraint on the system, we just integrate Newton's second law. So we are somehow preserving the energy of the system. The energy of the system is constant. However, it changes because of the error of the numerical calculations, but we can say that we give them constant energy, and we call it NVE in symbol, which means that the number of the atoms, the volume of the simulation box, I will talk about it, and the total energy of the system. Okay, but if we have the temperature is sometimes fixed. For example, you are, for example, simulating something near a heat bath. near environments. We have to use NBT ensemble, in which the number of atoms, the volume, and the temperature is constant. And most of the simulations actually are NPT ensemble. Okay, they are the pressure and the temperature of the environment is fixed. So we have to run the simulation at constant pressure and constant temperature. This is, for example, an example. We have a membrane, and this is a nanotube that has inserted into the membrane to transmit drugs. And so because it's in the body, it has a fixed temperature and it has the internal pressure of the body. Okay, as I told you, now we have to intervene to the integration theorems. One of the easiest way is that, as we know that the temperature is related to velocity, we just scale the velocities so that it reaches the overall temperature. Okay, it's really easy, but on the other hand, it's so rigorously, you're intervening to the system of the atoms, so it's not really stable. And usually used when you want to increase the temperature of the system very fast, and then you will do some other integration theorem methods to stabilize the system. We have other systems, no-solver, Langevin, Burns, and no-solver is the default for class. So if you want to use no-solver, there is no need for extra settings. And that is the no-solver. Actually the basic idea is a little complex, but it is that, the calculation, the basic idea is not. It's actually based on extended system. It couples the system with an external feedback. It gives another degree of freedom to the system. And you see that the simple equations of velocity rarely becomes a little complicated. We have the same thing for MPT ensemble. We have Anderson-Bernsen, and this is the one which changes the shape of the simulation box. Okay, so I want to, just as an overview, we want to check and then we go to a break. We want to check the general framework of molecular dynamics. So we have the initial configuration and initial velocity. From that, we evaluated the potential energy of the system. Then, with the derivative of potential energy, we evaluated the forces on each atom. From that, we had the initial velocity, the initial configuration, the initial acceleration, and with integration terms, we go forward to a further step. In this step, if we have any constraint, we should apply on the time integration. Then we calculate the desired properties, we should explain on this point, and then we move forward on the time. And this procedure is repeated until, we reach the desired properties that we want. Okay.
What are the properties you want?
Let's see. Yeah, it's finished. Okay, they are the properties. Okay, now we know the two molecular dynamics. So we can use more time on that. We know the position and velocity of the system. It means that we know the system completely. We know everything about the dynamic properties of the system. Okay, but the bridge between the microscopic properties and macroscopic properties is actually the statistical mechanics. We use the statistical mechanics. Of course, we don't actually use it. We just ask the lamp to produce that for us. But we should pay attention to what properties, the correctness of them exactly affect the macroscopic properties. But for example, we have the position and velocities. We have an equipartition theorem that from the velocities you can find the temperature. We have Virion theorem, which is more favored for mechanics and for engineering, that we can find the pressure and stress of the system, and so many other things. For example, if you know the stress of the system or the pressure of the system, for a given deformation, it means that you have the stiffness. Okay, so this is the mechanical properties of it. The basics is a little chemistry, but it's really used for mixing mechanical properties. Okay, and there are some references for the molecular dynamics. Again, everyone. I think I'm going to set a little near to the microphone so you have my voice more clearly. Okay, that was actually the first part, was the part that was related to the basics of molecular dynamics simulation. But okay, this is the topics of the next day, but I'm going to a little talk about it. They are the techniques that are used in molecular dynamics. It's not actually molecular dynamic itself, but they are frequently used to reduce the expense of computations. Okay. And then I think for tomorrow, sorry, for the third day, we can explicitly just work on the lab software itself. Okay. The first thing is a periodic boundary condition. You know, we cannot simulate a large. Okay, sorry. We cannot simulate a large scale of atoms due to the computational expenses. So we can simulate a limited numbers. Is my voice clear? Okay, so we can simulate a limited numbers, okay? But the problem is that simulating a limited numbers may produce artificial surfaces. It will produce artificial size effects. You know, at a lower scale, it's really important. What is the scale of the system you're simulating? To do that, to overcome this problem, we are using the periodic boundary condition. The whole idea is actually quite simple. And we have a central cell, that is the simulation cell, and we exactly replicate the cell in other directions, which are called the image cell. Okay? And the criteria is that whenever an atom moves and exits the simulation cell, the central cell, an exact atom with the same velocity enters from the opposite side. So in this way, actually the boundaries of the atoms are open. They are not closed, okay? So we are simulating just a cell, but actually it's representing a bulk state. Also, we have something called cutoff radius, okay? To find the potential energy for an atom in a system, first we have to calculate the distances, and then we should calculate the potential energy between these distances. But sometimes the distance is so far from an atom, okay? So in the, for example, it comes here, it should be there. So for example, in the Lennard-Jones potential, this is here. It still has values, but it doesn't have any effect on the results. So what should we do? We define something, a cutoff radius, beyond which we are not calculating the potential energies for this, okay? For example, from this part, if it goes from this distance to this distance, we are not calculating the potential energy anymore. But there's a problem here, that there is a discontinuity. And when the potential energy has discontinuity, you know, the force, which is the gradient of the potential energy, has problems. And there are some methods to conquer this discontinuity. For example, a shifting method. They shift the potential energy up because, you know, the changes in potential energy is what is important for us, okay? Not the exact value of this. They shift the potential energy up so that, for example, it becomes equal to 0, but it still has problems because maybe the value of potential energy is 0, but the gradient, which is the force, is not still 0. So sometimes, for example, they add some parameters. They add something like a shift, they add a function, like a switch function, that it smoothly, for example, comes from 1 to 0. It is multiplied, but in that way, for example, we change the, I don't know if you understand this one. We have a function, we multiply a function to this function. Your internet connection is unstable. Is it okay? Okay. Okay, but it will change the form of the potential energy. So there are some other suggestions. They just, for example, apply the switch control function in a very small step, in a very small distance. So it doesn't affect the total potential energy just near the cutoff radius. But the problem is that, so we don't want to calculate potential energies for the atoms that are far from the cutoff radius, but we still have to calculate the distances to know which of them are in the cutoff. So we still have a lot of computation to do, okay? For this, there is a solution called the neighbor list. We build a neighbor with a skin beyond the cutoff radius, and we just calculate the distances between the atom and the neighbor, okay, to see if they are inside the cutoff radius or they are outside the cutoff radius. Because sometimes, you know, the atoms doesn't move so much. For example, we have a solid, we do not have a high temperature, so they don't move so much fast. You build a neighbor, and then you just check if the atoms come to the cutoff radius or not. And then, for example, every 10 to 20 time steps, you just update this neighbor list. Okay, this is something that you will go hopefully to see in the LAMS script, that you can modify this neighbor list. Okay, and also at the beginning, I told you that we have an initial configuration, okay, but we didn't say from where we bring this initial configuration, because it depends on the materials. And we have different softwares for different materials. For example, if it has a crystal structure, it can be BCC, FCC, HSP, HCP, sorry, SC. That's, I think that just polonium is the metal that has simple cubic form. The crystal structure is actually implemented in LAMS. You know, we don't need to, you can import it from other softwares, but it's not really needed. We may have carbon nanostructures, which is graphene, fullerene, and carbon nanotube. I think you are all familiar with carbon nanotube. The graphene is, again, they have the same structure. This is just a plate. This is hypothetically rolled. When we roll the graphene, we have carbon nanotube, and we also have fullerene. It is also an allotrope of carbon, but the carbon atoms form spherical here. We also have, for example, nano-onions. There are multiple layers of fullerene inside to each other. For this, tomorrow, I don't know, maybe today, let's see, we can build carbon nanotubes in the softwares like VMD, nanotube builder, and it is really common. So we have a lot of software for this. And also these are some websites you can use to build the initial structure for carbons. It can be polymer nanocomposites. The famous software is Material Studio. Of course, it's not open source. And also you can build it in Argus Lab, or you can import it from different websites. And also, you know, we can have membranes initial. This can be built, it's a membrane. It can be built using VMD. If we have time, maybe we build a membrane in VMD together. Okay, and it is, okay, the basics is finished. So I think the next session, we are going to implement LAMS. Have you received the email about installing the software? And could you install it? Just some simple clicks, of course. You didn't try. And the installation is nothing, actually. The serial version is quite easy. You just click and it's just, actually, it's, yeah, it's just extracting some files. It's not really complicated. The MPI version, it just has some tricks. But if it doesn't work, we will see. If you could bring your laptop, do you think that you can bring your laptop on the last day? If you didn't bring, it's okay. Just maybe it's better. But we have, you know, a limited number of plugs. So if someone doesn't have it, it's better to have your laptops charged. And also VMD. VMD is the visualization software. We write the codes in LAMS, we visualize it in VMD. Okay, and I think I'm going to explain the script that day. Thank you so much.